with a rank of journals, but I just want to encourage you really try something ambitious from Science and Nature for last 2 weeks.
We have another presentation.
We do?
We do, yes.
Whose?
Yeah, because
You?
no, because Dr. Suits would go on for a couple weeks during the
Is it,
semester. She's making up the classes that we missed on Friday, so for about half of the semester, I can only come to about half of this week. After that,
But we have presentation from.
It's very informal, yes. Oh, the camera is tired of us. If it will fail, then we'll watch on the small screen. And it's only for those who are really curious.
Is it, maybe it looks like it's more like a
Something.
No,
is
it's
like-
not contact. It goes from this computer. It's just because lamp is overheated and it will burn soon.
Maybe.
Turn it off and
It will do.
Let me just look on your.
It will do. Yes, it will delay
Because
substantially.
This is impossible.
Yeah, do not look there.
Just switch off. Let it
Then
let
it
it
will
cool
cool
Yes.
down and we can use that for after a while.
or
So who is interested, they will hear. And I will send the slides if needed. So there will be no detailed introduction. It's more technical. So introductory part was done partially by Braden on Tuesday. The graphene and other two-dimensional materials have unique properties that attract attention, and one of their properties is that some states, in some states, mass of electron and hole approaches zero, and which means it becomes infinitely easy to excite them. On one hand, on another hand, there are some states in magnetic field. You know, in magnetic field, the charged particle with velocity changes its path to curvilinear, and those circular trajectories potentially can carry information. So what I am going to show will be computational modeling. So it's not ab initio, it's just modeling of just little codes. How the quantum state of an electron in a graphene changes with time. So this little modeling shows electron distribution, like square of wave function, not as function of position in x and y, but as function of momentum, right? So if we create a plane wave with certain momentum in certain direction and look on this diagram, in absence of any external perturbation, no optical excitation, no magnetic field, no lattice phonons, it should stay, the peak should stay where it was. It shouldn't move at all. So this diagram will represent just a plane wave that doesn't change in time, on one hand. On another hand, this would be correct for anything, graphene, and our reference point, the free space, free two-dimensional space. The difference between real material and two-dimensional space is momentum distribution. So how the kinetic energy depends on momentum. In the free space, two-dimensional space, energy is square of momentum. Kinetic energy is square of momentum. So it is like an inverted bell, right? And one doesn't need any computation to get it. In the realistic materials, the dependence of energy of electron on momentum is either derived by some advanced analytical formulas or computed through ab initio computation. So if we compute like energy of LUMO as function of k point, it will be dependence of kinetic energy of electron on the momentum. Very often, this shape will be substantially different from what we have in free space. So it will be not an cup or inverted shape, but it will be something exotic. So for graphene, this shape, which is shown by these meshes, it looks like peaks, 6 peaks with 1 peak in the 7 peaks, one in the center, and then there are dips between them. So the dips look very sharp, like a beak of a bird, very sharp. And if one builds the same figure for the occupied, for the HOMO, it will be peak facing upwards. So the electron and hole dispersion curves will touch each other at specific points. The points where this big form or cones touch each other are referred to as Dirac cones, and they appear not in any material. It is rather exotic. So there are much more materials that do not have these Dirac cones. Like cadmium, selenium, silicon will not have them. So it's only in very few materials. And the presence of these Dirac cones make these materials especially interesting. So what this simulation does, there are two-dimensional curves. One is this transparent mesh, which shows the dispersion, right? And you see a little peak, maybe you do not see from this distance, which is wave function as function of momentum in x and y. So it looks like Gaussian shape with very narrow, peaked in some point. In absence of external perturbations, it will just stay unchanged. If there are external perturbations, and here it will be on the magnetic field, it is expected to either start curly motions on a circle if magnetic field is strong, or if magnetic field is a little insufficient, then it may form some quantum states and form interference patterns. There is another feature. So this background level, you see it is a little higher than this Dirac points. So it is expectation value of total energy for this quantum state. And if energy, kinetic energy, total energy must be conserved, but kinetic plus potential kinetic plus potential conserved. But if you look only on kinetic, it may go a little up and down. So you will see that it moves a little bit. Make sense? Okay, so it will move. I didn't let it move while I was speaking, but so you see the peak becomes less sharp, and it starts distributing in this forest of the peaks. It's not very visible, but this figure is needed for definitions, what is what. Okay? So here's the similar figure. You see this peak goes down, and then it splits, starts distributing, and expectation value of energy is changing. So the areas between this inverted bells is where wave packet is allowed to move. The areas, it cannot climb to the top of this potential, well, it's not potential, but kinetic energy distribution, because it doesn't have sufficient energy. But this diagram is, as you already noticed, hard to see. First, because it is a small screen and you're sitting far. And second, because it's too many information. What if you look on this diagram from the top? Then this mesh, they also color coded, but it is not much visible. But the blue area shows continuous color, the isosurface of this excitation, expectation value energy, and this yellow color is the position of the wave packet. So this yellow stuff will start moving. The red spots are the Dirac points, D points, or peaks of the Dirac curve. So there is also something not ideal in this figure, that it is rectangular. Since unit cell of graphene is non-orthogonal, the Brillouin zone in K-space should be also, well, you see some motion, right? And it moves according to the corkscrew opener, right? From X to Y to Z. No? Okay. So one should look onto these diagrams only in this area of definition. So away from this hexagonal, it's not right, and calculations should be done not on the bigger grid, but only inside this hexagonal. So we start at one Dirac point, and as time passes by, this peak moves towards another Dirac point, and it overcomes a barrier, so to say. But we can screen different, and now it stops, just because simulation is done. So what I'm going to show is screening different values.
Does it go on the circle?
It will go, but it will overheat the poor laptop. And the file for this single simulation with this resolution is already like 100 megabytes, which is a little heavy. So the rest of these lights, and there are about like half dozen of them, will show this little circle moving along the bar line, which will correspond to different value of magnetic field. When it is very small, the wave packet in momentum space will not go anywhere from this initial Dirac point. If we go to extremely large values of magnetic field, it will start rotating like crazy. And in between, there will be something to look at, right? What else?
Let's look on it.
Yes, let's look on it. But after we look on it, we are not interested in anything else. It's the same. Okay, so small.
Does it make the full circle or half of this one? Like
It will make full circle, according to Lorentz force and classical mechanics, electrostatics. In real life, this is a little guinea pig. In real life, one should excite wave packets in all 6 points, and then they will move simultaneously. But it creates aberration, and then it is a little hard to analyze what is going on. So small value of magnetic field, you see that it just starts being distributed a little, and if magnetic field is absolutely zero, then it doesn't change the shape. Now it feels the walls of this, so to say, potential, reflects back and forms patterns. It's rather boring. Some patterns, some distribution. Not done. Okay, about done. Now let's go to different, bigger field. So it is expected that it will protrude further away from this Dirac cone, and because of the higher energy, amount of the fringes is expected to increase. So originally it splits on 2, and if we wait long enough, maybe there will be in both X and Y direction more fringes. But right now, so the whiter areas, they are peaks. The darker areas is covered where the actual cones, and transitions between them are, between peaks, are like barrier. So in order to start moving, there should be sufficient energy to go from one Dirac cone to another one. So this value of magnetic field is not sufficient, although it increases overall space or momentum space that it covers, and then simulation stops. Okay, let's go a little further and see larger values. And this is about intermediate value when it's almost penetrates both. What is interesting, for very large value of magnetic field, it starts moving clockwise or counterclockwise depending on the value of magnetic field, right? Positive or negative. But if it is small values of magnetic field, it reflects from the walls, and instead of moving in one direction, it forms fringes. So it's kind of oscillating within this well. And everything with magnetic field bigger than that will make one or another form of circular motion. So at a very initial time steps, there will be repetition of formation of these patterns, and as we go further in time, the clockwise and counterclockwise parts. So this here is the magnetic field is negative, so it moves the clockwise. So you see the major peak is closer to the next Dirac point. So for this value, it should be sufficient to move away from original and distribute, start taking all space. So it passed the next and goes to the second next Dirac point. And the explored time is approximately the same in all simulations. So as we go further, it will move quicker and protrude further. So here the value of magnetic field is positive, and you see it goes next, second next, and it splits on two wave packets, and it kind of comes on the opposite side of this clock. And now it looks more vivid. So the major peak comes counterclockwise, but they meet at the opposite side and then form rather random interference pattern. But this is the quickest one of the available, and it looks very vivid. But it looks that the primary peak stays distinguishable for relatively long time, and it moves on the circular orbits, how to say. Following Javid, this is prelude, and there are no conclusions. The next step is observe to make some notes on how the qualitative behavior of this wave packet depends on initial magnetic field value and on the width of the distribution, because changing the width also will affect. So it can either form patterns in the vicinity of this Dirac point, or it can start circling. And in between, there are several interference figures. Done? Any questions?
I need the motivation on Tuesday. Can you say
Motivation on Tuesday?
like why this is interesting? I didn't hear phrase.
Moving clockwise, counterclockwise will be like 0 and 1 bits, states for carrying information, and their superposition will be qubits.
So you're trying to use this for creating bits
Right.
for the quantum
Yes.
computing.
Yes.
But you think that this can be done at zero temp? I mean,
Well, to
at
do
room
that,
temperatures?
no. This can be done maybe up to like 5 Kelvin.
Oh.
Hmm.
But then
graphene. And graphene is not noble. Nobel Prize for graphene, including the exploration of formation of these Landau levels, was already claimed and received by Game and Novoselov
2010.
in 2010.
We have
But-
9 years.
Yes, we are 9 years late. But right now there is a range of other materials who may exhibit similar properties at much higher temperatures, and they are in the same range. They are composed of the elements in the same range as our favorite, like cadmium selenide materials that show interesting behavior. It's maybe
But
bismuth.
do they
selenide.
need to have the
Yes,
the
yes.
cones, but
It-
cadmium, selenide?
Cadmium, no, but nearby
Ah.
elements.
Just molybdenum disulfide? Or
No,
that-
no.
It's the 2 layers, but
That's
not the Dirac.
Not any two-dimensional material will show
Yeah,
Dirac cones,
yeah, yeah.
but the Landau levels can be created in most of two-dimensional materials.
So I'm just wondering, maybe it's a stupid question. So is this
I
property
can provide a stupid answer.
the relativistic effect of electrons by
Yes, it will be affected a lot by relativistic, and here I went careless. Probably at this range of these values of magnetic field, the pace of this rotation will be already at relativistic range, and when one would need special corrections.
So why
So
do we-
at the lower values, these calculations can be trusted. At higher values, they can be maybe not complete garbage, but a strong approximation.
so in practical, is that the reason that it need very low temperature? Maybe
No.
relativistic
No.
effect is very small in that case.
What is the barrier height?
I'm not ready.
Yes, but like if the barrier height is small, then.
The temperature means that nuclei will start moving,
Oh,
and
okay.
it will be
Interact with electrons?
deconstructive interference that will break anything.
Hmm.
So it's a nuclear.
The graphene has 6 Dirac points, all of them away from gamma, right? So minimum is when electron has non-zero momentum. This bismuth sulfide has Dirac coin at gamma, which means these quantum effects can be observed with lower energy, and there is only one cone. So probably there is a connection with the fact that one can observe interesting quantum effects at higher temperatures.
And you use the same methodology as we used way back when we did
The wave
quantum
back.
mechanics? Yeah.
It is.
Time evolution.
It is.
Okay.
It is time evolution with evolution
Technically,
operator.
you can, why use, and you can use it and calculate it in gamma for the bismuth case, right? I mean,
Yes.
to the
When just from ab initio calculations, one needs the dispersion curve. Without dispersion curve, huh?
But this is known, right, for bismuth, sulfide or whatever it is.
Today, yes, but who knows what will be the next material of interest. So I need a procedure of reliable procedure of extracting dispersion curve, feeding it into quantum
In other
calculations.
words, you need someone who will calculate VASP through many key points and provide you this.
Exactly,
potential.
and it was what was offered by Braden.
And you try
Tuesday.
just to ask who is interested in doing these calculations. This is your goal.
Mm-hmm.
I know Braden will be interested in it.
Yeah.
He's already doing it.
Ah, oh, okay. For bismuth.
No, he doesn't know about bismuth yet. Maybe.
Using graphene or not.
Well, he's done graphene, but if he will be offered bismuth, maybe he will do it as well. Okay.
Any other questions? Suggestions?